Welcome to AI Paper Slop. We're getting absolutely straight into a paper from June 2026 today, and it's called Agentic Real2Sim, Physics-Based World Modeling with Vision Language Agents.
Right, and the core insight here is just a total game changer for robotic data. They basically tackle the nightmare that is real-to-sim conversion. So instead of manually aligning coordinates and, cleaning meshes and tuning physics, they've built a fully automated framework.
Yeah, it uses vision language models, or VLMs, to convert raw videos of robot interactions into these simulatable episodic twins.
Exactly. And the real bombshell, the thing that's going to make everyone listening rethink their compute budget, is that they restricted the VLM to just orchestrating deterministic tools. It's not doing the physics itself.
Right, and because of that, an open-weight Gemma 4 3-to-1B model actually achieved a higher replay success rate than GPT 5.4.
Yep. At literally 3% of the cost.
3%. It's wild. So in this deep dive, we're going to cover exactly how this agentic pipeline is structured, the specific perception tools it relies on, the rigorous VLM judge evaluation on the DROID dataset, and how it generalizes to deformables and humanoids.
It's a lot of ground to cover, but to really get why this matters, we have to talk about the baseline. Like why Real2Sim has historically been such a massive bottleneck for policy learning.
Oh, absolutely. It's always treated like a plumbing problem, right?
Yeah, a plumbing problem that just fails in practice. People think, well, we have tons of video data and we have great simulators like MuJoCo. Just pipe one into the other.
If only it were that simple.
Right, but a physical interaction episode isn't just a static 3D scene. You have to extract the robot's trajectory, the object states, the physical parameters, the camera setups, the task description, all of it.
It's honestly like trying to bake a cake by manually reassembling individual crumbs.
That's a great way to put it.
Like right now, engineers have to do this manual labor of tuning foundation models, cleaning up meshes, and just gluing together these really brittle workflows across different perception tools.
It doesn't scale. You can't build massive simulation data sets if a human has to hold the pipeline's hand the whole time.
Right. So Agentic Real2Sim comes in, and the goal is to just take a single real-world recording and automatically output a simulatable artifact.
Without a human in the loop, it preserves everything needed for downstream robotic learning.
So, using that cake analogy, instead of gluing crumbs together, it's like having a head chef, which is the VLM managing a kitchen full of really highly specialized appliances.
That's exactly how the architecture works, and it does this through a 4-stage agentic pipeline.
Okay, let's trace this out. How does this head chef actually manage the kitchen? What is stage one?
So stage 1 is the visual processing agent. It starts by taking frames from the primary camera of whatever data set you're using.
Say raw pixels.
Right, raw pixels. And it uses SAM3 for open vocabulary segmentation, so it's isolating the objects in the scene.
But SAM3 just gives you 2D masks, right? Simulators need 3D geometry.
Exactly. So it hands those masks over to SAM3D for mesh recovery. And while it's doing that, it brings in foundation stereo to handle the depth.
Got it. So that gets the scale right.
Yep. And then for the temporal aspect, because this is a video, things are moving, it uses foundation pose to track the 6D object pose over time.
Okay, but what happens if the mask is just garbage? Like if the robot's arm is blocking the object?
That is the genius part of stage 1.
Yeah.
It has a retry budget. There's a mask critic built in.
Oh, wow.
Yeah. So if the VLM looks at the mask from SAM3 and says, this is heavily occluded or there's too much motion blur, it just rejects it. It picks a different keyframe and runs the segmentation again.
So it's not just blindly executing a script and hoping for the best?
Right. But even with perfect visual geometry, you hit a wall. MuJoCo doesn't just need shapes. It needs physics. It needs to know how heavy the thing is.
Right, because dropping a pixel-perfect feather looks identical to dropping a pixel-perfect brick if you don't know the mass.
Which brings us to stage 2, the physical prior inference agent. The VLM looks at the visual evidence and infers simulator-facing priors.
So it's guessing the materials.
Basically, yeah. It identifies the object identity, the material class-like, is it plastic, is it metal, and it provides mass hints.
Just based on its broad training data.
Exactly. And once you have the visual state and the physics priors, you move to stage 3, the scene preparation agent.
Okay, this is where it all actually gets loaded into MuJoCo, right?
Yes. It Calibrates the cameras, it aligns the robot base pose against the robot mask, and crucially, it estimates the ground plane.
Oh, ground plane estimation is always a nightmare.
It is the absolute breaking point for most automated pipelines. If your ground plane is off by even a millimeter, your simulated robot is going to smash its arm into the table.
Or just grasp at empty air.
Right. And visual tools, even state-of-the-art ones like foundation posts, they have visual noise. They will have millimeter-level errors.
How do they fix that?
Stage 4. The simulator-in-the-loop grasp optimization.
Okay, break that down.
Instead of just trusting the visual pose estimation blindly, it runs a deterministic sweep inside the physics engine. It basically tests a bunch of candidate microshifts.
So it's moving the objects, like a tiny bit to the left, a tiny bit right?
Exactly. It shifts it, rotates it slightly, and then actually runs the simulation to check the contact outcomes.
Oh, I see. So if it shifts it left and the object clips through the table, it throws that placement away.
Yep. It only keeps the placement that allows for a successful grasp in the physics engine.
That is super clever. It's using the simulator as a validation tool for the visual data.
Exactly. It closes the loop.
Okay, I have to push back on something here, though. The word agentic is such a buzzword right now.
No, it's everywhere.
Right. Half the time it just means someone wrote a Python while loop. So when they call this Agentic Real2Sim, is the VLM actually, understanding the physics? Is it calculating these 60 poses and his weights?
No, and the authors are very explicit about this distinction. The VLM does not do geometry. It does not do physics.
So what is it doing?
It acts purely as a decision maker on ambiguous data. It's handling bounded, schema-constrained queries like, which object is the robot manipulating? Or, is this mask clean?
Right. It's the head chef.
Yes. The deterministic specialist components, SAM3, foundation pose, they do the heavy lifting. The VLM just orchestrates.
Okay, so because it's so strictly scoped, that must be why the compute requirements are so low.
Exactly. And that leads to the most surprising finding in the entire paper, the VLM showdown.
Right, let's talk about the experiments on the DROID dataset.
So they took DROID 100, which is a subset of the DROID dataset. It's all rigid object manipulation, different objects, cameras, verbs like pick, place, push, insert.
And they just swapped out the VLM to see who could orchestrate this pipeline the best.
Yep. And the results are just wild. They tested Gemma 431B, which is an open model. It achieved 48 successes out of 100 episodes.
Okay.
Qwen 3.635B got 45. GPT 5.4 got 43, and Claude Haiku 4.5 got 37.
Wait, really? GPT 5.4 got beaten by a 31 billion parameter open model?
It did. But here's the kicker. The cost. Running 100 episodes through Gemma cost $2.62.
Wow.
Running them through GPT 5.4 cost $82.30.
So GPT 5.4 was over 31 times more expensive, and it performed worse.
Significantly more expensive for worse performance. But we should probably explain the evaluation metrics so you know those success numbers are real.
Yeah, how do they actually define a success? Because it's not just a vibe check, right?
No, it is a brutal scoring system. They use 3 independent VLM judges. They send these judges the start, middle, and end keyframes from the simulator alongside the real-world video.
Okay, and they scored out of 10.
Out of 10. And they subtract points for very specific failures. If it identifies the wrong object, that's -4 points.
Ouch.
Wrong final location is -3. Wrong action is -2. And wrong end gripper location is -1.
So you need an 8 or higher to be considered a success.
Exactly. It has to be highly accurate geometrically and temporally.
Okay, but I have to point out the elephant in the room here. Right. Even the best model Gemma only hit a 48% success rate.
Right.
If I'm an ML engineer listening to this, I'm thinking, okay, a 52% failure rate. That's terrible. Does that make this useless for actually building data sets? Like, I don't want to train a policy on broken physics.
It's a fair question, but you have to contextualize where the failure is happening. The sub 50% success rate across all the backends proves that the bottleneck isn't the VLM's reasoning.
Oh, because if it was the reasoning, GPT 5.4 would have crushed it.
Exactly. The framework proves that you can automate the orchestration. The failures are coming from the upstream visual perception tools.
So like if foundation pose just loses track of the object for 3 frames because of a heavy occlusion, the whole simulation fails.
Yep. The deterministic tool dropped the ball, not the VLM. But because the VLM is just a cheap router, you can default to open weight models for massive batch conversions.
I see. So it changes the workflow from deterministic to probabilistic. Like, if I need 1,000 perfect simulation episodes, I don't try to manually hand-tune 1,000 videos. I just run, 3,000 videos through Gemma for like $80.
And let the strict judge system filter out the failures. You keep the successes.
Mm.
You could never afford to do that with frontier models.
That makes total sense.
Yeah.
Okay, so that's all on the Deroid dataset, which is rigid objects, mugs, blocks, stuff that doesn't bend.
Right, which is mathematically much easier for a simulator to handle.
But the real world is squishy. So how does this generalize to, like, deformables or entirely different robot bodies?
This is where the framework really flexes its modularity. They applied the same core episode contract to deformable manipulation using a fist twin style setup.
So they're dealing with rope, cloth, elastoplastic materials?
Yeah. Obviously, you can't use rigid 6D pose tracking for a piece of cloth.
Right, because the distance between points on a cloth changes. The math just falls apart.
Exactly. So the VLM just routes to different tools. It replaces rigid pose tracking with tracked particle states, spring dynamics, or mesh states.
That's amazing. So the orchestrator doesn't change, just the appliances it uses.
Right. But validating a grasp on a deformable object is harder. You can't just do a microshift, so they use simulator rollouts.
Oh, so it actually runs the simulation forward and compares it visually.
Yes, it checks if the bending and stretching in the physics engine matches the visual deformation in the video.
That is wild. And they didn't just stop at materials, right? They did humanoids too.
Yeah, they applied it to Unitree G1 humanoid clips using a BFM0 style approach. They retargeted motion from the LOFAN1 dataset.
Just to give some context for you listening, LOFAN1 is this massive dataset of human motion, capture locomotion, kneeling, standing.
And transferring human motion to a robot is really hard.
Yeah, a human and a Unitree G1 have completely different joint limits and mass distributions.
Exactly. If you just copy the joint angles, the simulated robot will instantly fall over. The center of gravity is all wrong.
So how does the VLM handle that?
It replaces the object-centric scene prep with motion context retrieval. It basically runs a closed-loop replay against the reference motion, constantly checking if the gross pose and the balance agree with the physics constraints.
So it's actively validating the balance in the simulator.
Yes.
If you're an ML engineer training a policy for a humanoid to, like, fold laundry, this is huge.
It solves so many headaches.
Right, because historically you'd need two separate massive Real2Sim pipelines for that.
Yeah.
One to handle the squishy shirt and another completely different pipeline to make sure the humanoid doesn't fall over while holding it.
Exactly. But now, this single episode contract handles both. It routes the cloth to the particle tracker and the balance to the motion context tool.
All automatically.
All automatically. So to summarize, Agentic Real2Sim really proves that we can wrap these deterministic perception and simulation tools in lightweight, bounded VLM agents.
And we can generate high-fidelity episodic twins directly from raw video.
And do it cheaply.
Which brings up a really provocative thought to end on today. Something for you to mull over.
What's that?
Well, the whole industry right now is obsessed with AI data scaling, right? Companies are spending hundreds of millions of dollars building these massive physical robot data collection farms.
Oh yeah, warehouses full of robotic arms just picking up cups.
Right. But if we can reliably and automatically generate physically accurate, simulatable twins from just raw video using a $3 open weight model, what happens to the value of those physical farms?
That's a great point. It plummets.
Exactly. We might be looking at a future where robotics aren't trained in multi-million-dollar labs.
Yep.
They might just be trained by feeding thousands of hours of random YouTube videos through these automated Real2Sim pipelines.
The data bottleneck is officially broken.
It really seems that way. Thanks for joining us on this deep dive into Agentic Real2Sim, and we'll catch you on the next one.